Let's get started. Previously, we learned about what is a solution. We learned about how to calculate the concentration of a solution. Today, we want to think a little bit deeper about the solution. We are going to introduce some terms, the physical chemistry terms, the entropy and the enthalpy, to describe the property of a solution. Okay, and after we understand that concept, and I want to predict whether it's going to form a solution. The next thing we want to know, what are the factors is going to affect the solubility? So basically we're going to tell you, okay, how the temperature is going to affect the solubility, how the pressure is going to affect the solubility. And then at the very end, we are going to apply all these things and summarize with one very famous equation called the Henry's law. Henry's law is a very simple equation, tell you, okay, if you know the pressure of certain species in the air, you can predict how much of that is going to dissolve in your water solution. So let's a quick summary of today's lectures. Then we can get back to your lecture notes. Let's talk about solution formation. Today you have substance A, substance B. In order to form a solution, the first thing you do is actually what? You mix them together, right? So the first step to form a solution is actually you need to mix your solute and your solvent molecule. Your solute and your solvent, they need to mix with each other. So one of the best example is actually if you mix two gas molecules together. Okay, for example, if today you mix, let's say your oxygens and the nitrogen together. So here what it shows is actually inside a box, it was divided into two empty space, and then in those empty space, I fill in oxygen and nitrogen. Then I remove the blocker in between. Then they're going to mix with each other, right? So what is our definition of solution in the very beginning of the class? Yes. So you need to mix substance. Have a homogeneous mixture in single phase. Then we call it as a solution, right? So based on that definition, that is actually a gas solution, right? Your nitrogen and oxygen that mix homogeneously in one single gas phase. So that is a solution. Based on your intuitions, you know these things will happen what? Spontaneously, right? So what does this tell you? If you have two things, okay, if they don't have specific interaction, once you just mix them together, this is a spontaneous process. And then many times you will heard these terms called the entropy. Okay, anyone know what's the definition of entropy? Randomness. So there will be actually another term we are going to go through, okay? It's called the enthalpy. Okay, these are two different terms. So we are focusing on the entropy now. Entropy is actually the term to describe how random the situation is. And the randomness is an indication of how possible one single event could happen. If you have a large entropy, that means you have higher likelihood to see those situations. Give you examples. Think about your room. In order to keep your room nice and clean, you need to put in a lot of effort to arrange all the items. So under that case, the entropy is minimized. But that requires putting a lot of effort to achieve that. Under normal situations, when I say normal situation, is that you don't really pay too much attention to the cleanness of your room. What happened to your room in the end? Things will go everywhere, right? It becomes very random. So if you have higher entropy, that means actually if the situation becomes more random, it's actually a preferred state in nature. So that means actually it's going to happen spontaneously. It's going to happen naturally. Okay, so that's actually one of the very important concepts that you want to have here, because if today you just mix things together, originally each gas molecules only have a small volume they can actually participate, all the molecules they have, right? So it's kind of constrained. But if today you actually give a bigger space for them to actually run around, then they have more possible ways to actually distribute their energies. Okay, in other words, they go to a space, they increase their possibility to distribute all different states they can actually have. So that's actually increase of entropy. Okay, so make this mixing process a spontaneous process. That actually leads to here. Okay, so why does the mixing happens? Is because in random particle motion, okay, these two makes the configuration of particle, which is this represent the entropy, right? Okay, and then we know the larger entropy, okay, typically you will see this S is preferred. Okay, that means it's going to happen spontaneously. In other words, if you look at the next sentence, mixing is a spontaneous process. If you don't consider the interaction between your solute and solvent, you just consider the mixing process. This process is always favored process. Okay, so use this concept. Let's go through a few examples. Okay, the first example is actually if today you open a perfume bottles, what's going to happen? You start to smell the perfume, right? So what does that mean? That means actually the molecule originally was constrained within your perfume bottles start to diffuse out. It start to mix with the air, okay, and this is a spontaneous process. Second thing is actually if you're spilling a bucket of marbles, what's going to happen? Originally the marbles were constrained within the bucket, right? You spill out, and then the marbles go everywhere, right? Because you have larger space and it's actually larger entropy for the marble. This tool definitely is actually a clear example for the mixing. How about the third example? If today you have boys and girls, they are at their first school dance, will they actually mix well? They won't, right? Why? Because there are some extra interactions between them. Okay, so remember when I said that mixing is spontaneous, that's actually a prerequisite for that, right? That means actually there's no interaction between molecules in the beginning. Okay, then we know after that conditions, the mixing is spontaneous. But under this case, okay, you know, in their first dance, they're actually repulsive. They prevent them to actually mix with each other. So under this case, we know these things probably won't happen spontaneously, but it's not because the mixing process. It's rather because there's some other interaction between the two entities. So that's actually about the mixing. The other thing is actually talking about this enthalpy term, which is actually more about the energies. In order to form a solution, if you think about the things in a molecular level, first you have your solute. You want to mix that, that means you to actually break apart your solute. In order to actually break apart the solute, most of the time you're actually dumping energy so that they separate from each other first. Assuming this is actually the final state, that is the initial state, then we know the delta H of your solute, which can be calculated from the enthalpy of your final state minus the initial state. Because in this process, dump in the energy, so that you reach your final state, right? So if you do this enthalpy of the final minus enthalpy of the initial, this one will be a positive number, right? Because if you know the final state has higher energy than the initial, if you calculate the energy difference between the two, it should be positive. So you know this typically is large and positive for ionic solute. The one good example is the salt, the sodium chloride. So we know salt is composed of sodium plus and chloride minus, right? And then because it's actually plus and minus, they have a very strong ionic strength between the two. So in order to form a solution, you actually bring those things apart first, and they require actually dumping energy. Okay, therefore, the delta H of your solute will be large and positive for ionic solute. You also need to do the same thing for your solvent. So again, to actually bring your solvent apart large enough so that the solute can actually fill in and then eventually form the solution. Under this case, using the same concept, the delta H of your solvent will also be a positive value, even though it's not large, but it's still you kind of break them apart. The delta H is going to be positive. So once you have separated your solute and the solvent molecules, then you mix them together. Once you mix them together, your solute and solvent, they are going to interact with each other. And that's where you're going to see this solution to form, okay? And under this case, once you form the bonds, you are going to form a lower energy species. So if you calculate the delta H of mixing, this one is always negative. If you have ionic solutions, it will be large and negative for the ionic solute solvent solution. So to summarize, to calculate the enthalpy change of your solution, it will be just the sum of the three terms. It will be delta H solute plus delta H solvent plus delta H of mixing. After combine all these effects, you're going to get your delta H of solution. If delta H mixing is the dominant term, then you're going to form the solution. But if today you have a dominant term of your delta H solute and delta H of solvent, that means you're going to consume a lot of energy to make the things to mix well together. Give you a quick examples if you go to next page. This is actually some of the delta H solution, means it's actually the sum of your delta H solute, delta H solvent, and delta H mixing. For your KOH, it is negative. The only term that gives you negative delta H is delta H of mixing. So under this case, you know, it's going to form the solution naturally. And then because it's negative, that means the heat will be released, because right now you're forming a very stable solution. It's low in energy, then all the energy that's above is going to release to your environment. So you will see the heat is going to be released to the environment, and the temperature of your solution is going to increase. On the other hand, for some other things, okay, you will see a positive value for your delta H of solution. What it means is actually you need to dumping enough energy to break apart your solute and solvent, okay, and those terms outweigh your delta H of mixing. That's why when you calculate your delta H solution, it is positive. So that's how you should actually understand this concept. Here is a summary, okay, about the sign of your delta H. If your delta H solution is positive, what it really means is, you know, you're going to have strong solutes, and solvent interaction. Basically, the first two terms, they actually break apart your solute, break apart your solvent molecules. And then they outweigh weak solute-solvent interaction. Under these conditions, then you are going to have a positive delta H. Then the next question is actually, if the interaction between your solute and solvent, if they are so strong, what causes them to break? So the answer is actually very simple. You need to actually dumping energy to make it happen. So typically you dumping heat from the surrounding. You heat up your solution so that it breaks apart. And you form the solution. Second is, we know mixing is actually always a preferred process. So it's actually a collective effect of both two terms that make you prepare your solution.